Now, today the topics I'm planning to discuss, if you remember on Thursday, on last Thursday, we started discussing electromagnetic waves. We had already figured out one possible solution of the Maxwell's equations. If you remember, we had this solution. The electric field at any point was E in the x0 direction cosine kz minus omega t, and B was B0 in the y hat direction cosine kz minus omega t, such that E0 should be equal to C times B0. And K over omega was 1 over C squared, or which turned out to be mu0 epsilon 0. So this we discussed already. Now today we will be continuing to discuss this wave a bit more. Now if you look at here, we have, well, there is an electric field, there is a magnetic field. We already know that the electric and magnetic fields, they have an energy density. So this Maxwell solution has energy. Furthermore, since this wave is moving in the z direction, the energy will be moving in the z direction. And hence there is a flow of energy. Now we will be discussing the flow of energy. That's the first thing we will discuss today. Now, of course, up to this point, we said that, okay, there is such a possibility that we might have a region of space where the electric and magnetic fields has this form. But up to this point, we didn't discuss how we can get such an electric and magnetic fields. Okay. So how do we get these electromagnetic fields? Now, this is the radiation by accelerating charges. Now, each one of these topics will probably take around 1 hour. So first hour we will be discussing this flow of energy. This is the second hour. And then there won't be any new subjects we will be discussing. So after that, most of you asked me to review circuits. So that's what I will be doing, a short review of circuits. Or any other questions that you might have. Now, before we start, do you have any questions? Do you have any questions about how we drive these electric and magnetic fields? Now, we didn't really drive these, we just guessed these solutions. Now, we just guessed that the electric field in a region, let's say it has this form, the magnetic field has this form. Then we ask the question, is it possible? I mean, if these are the electric and magnetic fields in an empty region where there are no electric charges or electric currents, then they should satisfy the Maxwell's equation with no sources, no charges, no currents. And we saw that they do satisfy the Maxwell's equations if these two conditions are satisfied. Under these conditions, then this is a solution of the Maxwell's equation. Now, this kind of changed our attitude towards the electric and magnetic fields. You see, up to this point, we were mainly saying that, okay, let's assume that there is this charge. This charge distribution creates an electric field. Then we said, okay, let's assume that the electric field is changing, so we create a magnetic field. The electric and magnetic fields, we always discuss referring to some charge distribution or some current distribution somewhere in space. But here we don't mention at all any electric charge or electric currents. Without any electric charge or current, it is possible to have such an electric and magnetic fields. Now, if you remember, we had written the electric density, the energy density stored in an electric field. This was given by 1 over 2 epsilon 0 E squared. Wherever you have an electric field, there is a corresponding energy density. Now we drive this relation for a special case when we consider the capacitor. We said, okay, so if we charge a capacitor, we have to do this much work. But that much work is nothing but this energy density times the volume of the capacitor. So we said that this is the energy density. The energy is in fact stored in the electric field, not in the charges. And for this particular solution, the energy density just becomes 1 over 2 epsilon 0 E squared cosine squared k z minus omega t. This is the energy stored in the electric component of this electromagnetic wave that we had discussed. Now then we also know that the magnetic field has a energy density, and we had derived it to have this form. And this turned out to be 1 over 2 for our particular solution. This is B0 squared cosine squared kz minus omega t. Now, but remember, B0 is nothing but E0 over C. So because if this electric and magnetic field satisfy the Maxwell's equation, this relation over here should hold. So B0 and E0, they are not independent of each other, they should be related to each other. So this tells me that the energy stored in the magnetic field would be nothing but 1 over 2 mu 0. Okay, B0 squared is E0 squared 1 over C squared cosine squared kz minus omega t. But remember, this 1 over C squared is nothing but mu 0 squared times omega squared. This whole thing is mu 0 epsilon 0. This is so the magnetic energy density is 1 over 2 epsilon 0 E0 squared cosine squared kz minus omega t, which is nothing but the energy density stored in the electric field. Now, when we started discussing the magnetic field, some of you were asking whether the magnetic field is stronger or weaker than the electric force, magnetic force. Well, not the force, but if you look at the energy densities, for example, in empty space, the energy stored in the electric field and the magnetic field, they just turn out to be equal. The strength, the relative strength of the magnetic and the electric fields will depend on the circumstances. This is a case where they have equal importance, let's say. No. Why should it be? Not necessarily. I mean, this is not the conservation of energy is that you measure energy, whatever form it has, you sum all of them at one time and compare the sum of all kinds of energy that a system has at a next time, at a different time. And these should be equal. That is what we call conservation laws. A quantity that has the same value at different times. Now, this is at the same time. At a given time, the energy density of the magnetic field in our solution is equal to the energy density in the electric field. This is at a given time. This is not the conservation. So the total energy, you can just say it is the sum of the two, or twice any one of them. The total energy density would be the energy density in the electric field plus the energy density in the magnetic field, or twice the energy density in the electric field, twice the energy density in the magnetic field, 1 over 2 epsilon 0 is, no, there's no 1 over 2. Epsilon 0 E0 squared cosine squared kz minus omega t. This is the total energy density stored in our system. That's not the total energy density at a given point. Remember, we define the energy density, energy per unit volume. If we want to calculate the energy in a given volume, we just have to sum this density over the volume. Okay, so your last chance to hand in your homework. Now, how does this look like? let's say as a function of z. This is the total energy density in space. Well, because we know that the energy density in the electric field and the magnetic field are equal. So at t equal to 0, let's say, at t equal to 0, it's just the cosine squared function with a maximum at z equal to 0. So this density just looks like this. It's not the same everywhere. It just changes as a function of position at a given time. This is at t equal to 0. Now, at a future time, it will just move. If you just put a positive time here, it will just have such a shape. Let's say this is the maximum. It's the same everywhere. If you plot the same function at a different time, it will look something like this. So it has, all the figure has shifted towards the right. That's why we say that it is moving towards the right. Now it has moved this much from here to here, the maximum point. Now, if you increase time, this point will just move further and further towards the right. I mean, this distance is supposed to be the same everywhere. Let's call it delta z. This is also delta z. This is also delta z, etc. All the points have shifted by delta z. It will not. It will not. It will never change. You see, if it has this form, you see, what is delta z? If you just follow this peak, this maximum, at t equal to 0, this was at z equal to 0. So this point, in fact, corresponds to this point over here. K delta z minus omega, let's say, after a time delta t, this is equal to 0. Or delta z is equal to omega over k delta t. You can consider any point that you like. If you would follow, let's say, this peak over here, that peak over here corresponds to k delta z minus omega delta t is equal to 2 pi. So it's just a shift. You just add delta z is equal to this number plus some shift. It's just linear motion with the same velocity. All the points on this shape move with this velocity. So the shape doesn't change. All the points move with the same velocity. Now, if you want to change the shape, what you need to do is you need to change this velocity over here. Well, does the velocity of light change? It does. If you put it in a medium, that's not, we will not be studying that here. And if you put this wave in a medium, if you say there's some glass somewhere and you shine some laser light through the glass, its velocity will be different, these shifts will change, etc. But we will not be studying them in this year. And you will study them in your third year. Now let's just consider a small fraction of this, a small slab over here. You see, we have these waves. If you remember, we draw the electric and magnetic field lines. They were just straight lines, infinite, going from minus infinity to infinity. So it's as if they just form a plane, all the magnetic field lines, and this plane just moves. That's why we call these plane waves. This is what we call a plane wave. Now, we have this energy density. So if you just imagine some volume over here, this volume will have a total energy in it. And this energy itself will be moving at the speed of light. So if you would define the flow of energy density, or flow of energy, we define as density, energy density, times the speed, velocity, this is how we define the energy flow. Well, in fact, any kind of flow, if you want to calculate the mass flow in liquid in a flowing river, for example, what you do is you define the flow of liquid as the density of the fluid times its velocity. This will tell you how much energy will pass in a unit area per unit time. That's what we are trying to calculate. Now, to see this relation, let's just imagine we have some unit area. Let's call it A. And how much energy passes through it in a time delta t. That's, if we want to calculate this one, what we can do is we can just consider this volume. This will be just C times delta t. All the energy in this region will pass through this area. Of course, we are assuming that this is the direction of the velocity of the object, perpendicular to the area. So all this volume will pass through, all the energy in this volume will pass through this area in a time delta t. So the total energy in this volume is the energy density times the volume over here, but the volume is A times C delta t. This is the total energy in this volume. Now, what we would like to find is the total energy that passes through a unit area, not an area A, but a unit area. So divide by A per unit time. The time is delta t, divide by delta t. So these cancel, A cancels. So what we are left with is this energy flow. It is the energy density multiplied by C, which is nothing but the speed of the electromagnetic wave we consider. Now, this flow of energy, we show it by S. S will be, we had already calculated the energy density, that is 1 over 2 epsilon 0. No, not 1 over 2. Epsilon 0 E0 squared cosine squared kz minus omega t times C. Well, this is one way of writing it. So what we are looking at is, this is the direction of the energy flow. We are, in this particular case, we are considering a wave moving in the z direction. So we just choose an area, and the question we would like to answer is how much energy passes per unit area per unit time. That's what we are trying to find out. So if we just, what we do to determine how much energy passes per unit area per unit time, you just take some area, pick up some time delta t, you measure how much energy passes through your area within that time delta t, you measure it, you can measure it, and then divide by area, divide by delta t, that will tell you how much energy passes per unit area per unit time. Since the energy is moving with a speed c, all the energy stored in this volume, which has an area A and a height c delta t, will pass through my area in a time delta t. So I just calculate the total energy passing through my area, divide by the area, and the time it takes for all that energy to pass through, then I get this flow of energy. Any questions on this one? Now we had defined, so if we show the flow of energy flow by the S, it has this form. This is the energy density. This is the speed at which the energy is flowing. Or we can also write this as epsilon 0, E0, E0 cosine kz minus omega t times E0c. Now, let's see. Let's say E0 over c cosine kz minus omega t times c squared. Now, the reason why I wrote it in this way is, well, this is nothing but the magnetic field. This is the electric field. 1 over mu 0 epsilon 0 times epsilon 0 E times B. Their magnitudes. Or I can also write this as 1 over mu 0 E times B. So if in a region of space you have an electric field, you have a magnetic field, there will be some energy flow in that region. Now, we had derived this result for a particular case of, in this form, I mean for a plane wave, but this expression just turns out to be true at all times. At any time, we will take one more step to obtain a more general result. Now, this is the magnitude of the energy flow, but energy flow also has a direction. It is moving in some direction. Now, in our particular case, energy is flowing in the z direction. You see, we had, if the electric field is pointing in this direction, the magnetic field is pointing in this direction, and the energy flow is in this direction. This is the direction of the energy flow, if you remember our initial solution. Now, let's look at this vector, E cross B. What is the magnitude? No, magnitude. No. No. The product of the magnitudes times the sine of the angle between the two. What's the angle between the two? 90 degrees. What's the sine of 90? 1. So we had obtained this vector S to be 1 over mu 0 EB, product of the magnitudes. Well, this we can also write as 1 over mu 0, the magnitude of E cross B. Now, the energy flow is in the z direction. What is the direction of this vector? It's also in the z direction. So if we define S to be this energy flow vector, this is 1 over mu 0 E cross B. This is called the Poynting's vector. It describes the energy flow through a unit area per unit time. It has the correct direction, the correct magnitude. So this is how much. This describes how much energy flows through a given region, through a given area. You will get bonus to make up for those questions. Now, any questions up to this point? Well, because the wave is moving in the z direction. That's the direction of the motion of the wave. You see, if, sorry, E cross. Now, you see, we started looking at the solution over here. So this solution at t equal to 0, it just looks like this. Now, as time goes on, what happens is all this pattern, this shape, just moves in the plus z direction. So from there, we can say that the energy associated with this energy density is flowing in the z direction. So our solution is moving in the z direction. Now, this is the solution, the derivation we had given here is just for a particular kind of wave. It's not really a general solution. But it turns out that this solution that we obtain, you can also obtain this solution starting from Maxwell's equations in general, and you will still get the same, exactly the same solution. This is the energy flow associated with a given electromagnetic field. So in any region of space, if you have an electric field, a magnetic field, then, and if this cross product is non-zero, in that case you have a flow of energy. Yes, this is the flow of energy. This tells us how much energy passes through a given surface per area per unit time. So this is also tells us that the electromagnetic fields has energy associated with themselves, not necessarily with other objects. So in this region, there is this the motion of the electromagnetic wave, and this is how much energy passes, is carried by that electromagnetic wave. The wave itself has energy. Now then there's the immediate question, does it have momentum? Well, the light doesn't have a mass, but do you need to have mass to have momentum? Why not? We define the momentum as mass times the velocity, no? So if mass is 0, no, I mean, let's stick with the ordinary momentum for the time being. Well, you see, in mechanics, we had defined momentum as mass times V. Well, we didn't discuss too much about, we will not be discussing special relativity this semester, but it turns out that this is valid only for massive particles moving slowly. That is, V over C should be much less than 1. Only in this case, this expression will be valid. Now let's remember Einstein. I'm sure we didn't discuss it that much, but I'm sure you already know this expression. mc squared. And this tells me that for any energy that you can think of, there is a corresponding effective mass. You can call it the mass, the effective mass. Now, light doesn't have this mass, but nevertheless, it has an energy. We already saw that electromagnetic waves carries energy. So if this is the mass, and if you want to calculate the momentum, let's say the magnitude of the momentum for the time being, what's the speed of the electromagnetic wave? C. This is E over C. Well, for an electromagnetic wave, we didn't talk about the total energy, which was not that much important, but we can still talk about the energy density, which will give us a momentum density. Similarly, the momentum density will be, you see, the flow of energy, or let's write it in this way. This is kind of the flow of energy. E times c, energy times the speed, kind of like the flow of energy. Well, the flow of energy is described by the Poynting's vector. This is the momentum density. So now we also have the momentum density of the electromagnetic wave. So it also has a momentum, not just energy. It carries momentum, it carries energy. But it should carry momentum. You see, if you, this electromagnetic wave, this special electromagnetic wave we considered has an electric field on its own. Imagine putting some charge in this electromagnetic field. Well, that charge, well, they have mass. If you send an electromagnetic wave, due to this electric part of the electromagnetic wave, it will accelerate. Its momentum will change. Since its momentum will change, either we have to give up on momentum conservation, because no other particle is gaining or losing momentum. It's only this charged particle that's gaining momentum. Either you forget about momentum conservation, well, that's not something we would like to do, or you should accept that the electromagnetic wave itself should have some momentum. And this is the momentum that the electromagnetic wave has. You see, this charged object is gaining momentum due to the electric field. So where does that momentum come from? Yes, true, but you see, it's the force that causes this change in the momentum, or the change in the momentum we call the force. But we said that given an isolated system, the momentum should be conserved. That's what we like about momentum. Isolated meaning there are no external forces. So here I have my system, electromagnetic wave plus the charge. There's no external effects. All is my system. My system, at least the charge in my system, is gaining momentum. So where does that momentum come from? Now the answer is, since the charge is gaining momentum, it is the electromagnetic wave which should be losing momentum. And we say that this is the momentum of the electromagnetic wave itself. So we had seen that the electromagnetic wave itself, although if you remember how we defined the electric and magnetic fields to start with, we said, okay, let's just define this concept. It was just a mathematical construct at the beginning, the force per unit charge. That was how we defined the electric field. We invented it. But now it turned out that it has its own energy and its own momentum. Just like an ordinary moving mass has energy and momentum, this electromagnetic field also has energy and momentum. So we say that it has its own existence. It's not just a mathematical tool that we invented, it actually exists. Now, any questions on this? Okay, now, if an electric and magnetic fields have energy and momentum, let's see. Let's imagine a stationary point charge. Then it will create some electric field around it. Does this electric field carry momentum or energy? So I have just a point charge at rest. Yes. In empty space, there is nothing. No, there is only my charge. So, does it have energy? Does it have momentum? Just a point charge at rest. Does it have energy and or momentum? If it has one, it will have the other one, but does it have it? I have this charge at rest. A single charge point charge at rest. Yes? The electromagnetic field, I'm not asking about this point charge. I'm asking about the electromagnetic field that this point charge creates. Does it have energy? Does it have energy flow? Does it have momentum? Okay, let's start with, does it have energy? Yes, so it has energy, because if I have this point charge at rest, there is an electric field it creates. Electric field has energy density, and hence this point charge will have the electric field created by this point charge will have energy. Is there a flow of this energy? So that would have been a problem if it had a flow of energy, because if the energy is flowing, I would ask, where does it go? Or does it just circle around my charge? In which direction? Or does it go to infinity? If it goes to infinity, where does that energy come from? Does it have energy flow? Yes or no? It shouldn't have, but why not? I mean, if you just look at our results, are our results consistent with our expectation that there shouldn't be energy flow? Are they? In which direction? Okay, how do you plan to apply the right-hand rule for a point charge at rest? Now, the point charge is not rotating. Well, let's see. The point charge creates an electric field, but there's no magnetic field. So there's no energy flow. There's no momentum. Well, okay, the problem is you cannot just create a charge over here. You have to bring it from somewhere else. Or let's just assume that it's just, we put it over here, wait for a very, very long time, such that everything is now, nothing is changing in time. In that case, there's no magnetic field, so there's no energy flow, and there's no momentum. Now, energy flow would have been problematic because we are looking at an electrostatic system. It shouldn't be changing in time. If it's not changing in time, it cannot keep losing energy, it cannot keep gaining energy. Of course, one possible thing to say might be that the energy flow is circular, but the problem with circular motion is that if you use the right-hand rule, the circular motion always tells you a preferred direction. They have a direction, they rotate around an axis. Now, our problem doesn't have such a preferred axis. The universe doesn't have a preferred axis. So there's no axis in our problem. It cannot rotate around an axis. Now, let's look at other static problem, magnetostatics. If you remember, we had discussed the constant current carrying wire, infinite wire. It creates a magnetic field. Does it have energy? We have an infinite current carrying wire, neutral, so there's no electric field, there will be a magnetic field. So does this system have, does the electromagnetic field in this problem have energy? Since the magnetic field is non-zero, we will have energy in the magnetic field. Is there a current energy flow in our system? Now the current is constant. Okay, there is a current, a constant current that creates the magnetic field, but there is no electric field. Since there is no electric field, there is no energy flow. Energy itself is stationary. It's not changing in time. Since there is no energy flow, there is no momentum. It's a neutral wire. You should just imagine this wire. This wire is neutral. There are negative charges flowing in my wire, but the positive charges are at rest. If you want to have both an energy flow and momentum for your given configuration, you have to have both an electric field and a magnetic field. One of them would not be enough. For example, if you just consider a single point charge moving with a velocity v. We have this charge Q moving with a velocity V. Well, we had already discussed the magnetic field. At this point, there will be a changing electric field, and we said that there will be a magnetic field at the same point. Do you remember the direction of the magnetic field at that point? Well, just imagine this as if there is a wire over here and there is a current flowing through the wire. So this is the direction of the current flow, so this will be the direction of the magnetic field. So here we have a magnetic field. What's the direction of the electric field? It's radially outward, more or less. Yes, yes. This is the magnetic field out of the screen. Yeah, here, at this point, this will be the direction of the magnetic field, and this will be the direction of the electric field. Now, what is the direction of the energy flow? Is there an energy flow? What is the direction of the energy flow? The energy flow is mainly in this direction, E cross B. And here, the energy flow. Does this make sense? You see, here, E cross B, this is the direction of the flow. At this point, this is E cross B, this is the direction of the flow. Does this make sense? Why not? Why? Now, let's also study 4 more points. This point, what is the direction of the magnetic field? And the electric field. What is the direction of the energy flow? And let's look at this point. This is the direction of the electric field. The magnetic field will be into the screen, and the energy flow. This will be the direction of the energy flow. Well, you see, close to the charge, both the electric field and the magnetic field are stronger, closer to the charge. So the energy density closer to the charge is stronger. So as this charge comes here, this region of space should have more energy than when the charge was over here. So the energy should flow through towards this point from somewhere. And these directions are nothing but telling us that the energy is flowing in this direction over here. This charge is moving away from this point, so the electric and magnetic fields at these points will get smaller. Since the electric and magnetic field in this region is getting smaller, the energy density in this region should be getting smaller. What happens to the energy density? It should have gone somewhere else. So these are why we have these directions are pointing away from this region. So the results do make sense. It's the energy from the back is from these regions, let's say, is flowing towards these regions. So what do you mean by bending of space? I only see energy flow. Now we are not talking about the space. We have some energy lumps, let's say energy lumps here. They are just moving forward. I mean, you see, just imagine it like this. Here are your homework. They are kind of distributed. As the charge is moving like this, some of these energy blocks are moving this direction. So there's no bending of space. I'm not bending space. Okay, any last questions before you go for a break? Analogs. Yes. I mean, if you choose to take elective course, I mean, gravity is not an obligatory course. But if you choose to study gravity in your graduate courses, you might see similar cases, analogs. Now, I am observing, according to the observer, this is what's happening. No, this has nothing to do with Doppler effect. I'm not talking about waves, nothing. It's just the flow of energy. The particle, the object itself is carrying the energy with itself. Okay, see you after 10 minutes.